Okay, we're going to continue just a little bit describing just a couple of details of the primary behavior, and then I'm going to go to the description of what we are going to do tomorrow, okay? And it's basically that, primary behavior in a very simplified situation. Okay, so let's say a couple of words about primary hull beam. So this is the side view, okay, of the ship structure, okay, and in this case we have pressure. In this case, it's not just hydrostatic; it's in general. Okay, this is dynamic pressure, and of course you have weight. This is W, and of course you have inertial load. So this is inertial load. Remember that in general, don't worry, this is we are not going to consider dynamics here, but in general, what we're going to usually do is we consider an equivalent loading, right? And that's because this, since this is dynamic, is not equal to that, because this is static. And the difference is there is an acceleration. So we need to consider that as part of this behavior. Now, since we are considering this as a beam, okay, the loading in this case has to be expressed, let me write it here, loading, P of X, okay, and this has units of force per unit length, okay? So that's what we need to consider, okay? Now, in the case of the pressure, okay, or the buoyancy, okay, it's something that we do. What we can do is we can take and a small here, let's take here, and a small segment of length delta X. So the buoyancy force, you see that this is big B. That means that it is total force. So it's going to be equal to the area of the hull, okay, multiplied by the length, which is delta X, and multiplied by gamma. Okay. Now, if we define B, this is buoyancy per unit length, that would be delta V large over delta X. So we put this on the left-hand side, and that's going to be equal to the area times gamma. Okay. Similarly for the other parameters, weight or inertial load. Okay. So you see that this is area, transverse area, and the other is just specific weight of the fluid. Okay, so if we go like this, then we will have the load function, and we will be able to calculate the response. Now, in this figure, people, take a quick look in this figure that this force here points upward, while this one here points downward. Similarly, on the forward end, this points upward, this downwards. And that's because in general, when we work with primary hull beam, we consider that this is a beam, but if the waves come from in an oblique direction, there could be some difference in the port and in the starboard and port sides. So in general, that means that this will generate torsion. Don't worry, we are not going to consider that. We're just going to consider a beam, a bending in the vertical direction. But you have to be aware that that could happen, okay? And not only that, okay, but also there could be some bending in the transverse direction, okay? So there could be some transverse bending, vertical bending, and torsion. We are only going to consider here vertical bending. That's enough, okay? Now, somebody remind me the equation, the equilibrium equation for the beam? Somebody? Equilibrium equation of a beam?
The second derivative of the moment is equal to the load.
Exactly. That's us. So that's what we're going to solve. Okay, second derivative. But in this case, we have to be careful because this is z. So this is going to be my. Okay. Now, here, this is a second order equation. So we need values at the top and at the end. And in this case, what we need is just to specify that m at 0 is 0 and b at 0 is 0. Okay. If we integrate from here to here until the end, since we have a static equilibrium, the two equations will be closed to 0. Okay. Now, what happens if somebody wants to integrate? Well, once you know the bending moment and the shear force, you can calculate normal stresses and shear stresses. Now, what happens if somebody wants to calculate the deflection? That's a problem that cannot be solved because there is no point where you know the deflection of the hull. That's all what we can do. Okay, we're going to mention something that it's common in this area. But let me tell you, that's all what we can do. We can describe the distribution of bending moment, shear force, but we cannot calculate the deflection. We do a simplification, and from there we get some values, yes. But that's all what we can do, okay? So let's not go now and explain what are we going to do, unless there is a question about this. There's no questions about this, then I'm going to go to. Okay, so let me. Okay, so this is what we are going to do. Can you see my white screen? Whiteboard?
Yes, doctor. Yes.
Okay. So this is what we're going to do. Okay, the lab is going to be about the floating bending. Okay, and you can see that the floating beam is the hull of a ship. But in this case, it's a very simplified hull. Okay, so we're going to consider a tube. Okay, so we have a tube. This. It's going to be floating or here. Yes. Okay. And what we do is we apply, we're going to apply 4 loads. Apply 2 forces in the central area, 2 others, and more or less like this. Okay, now this is X. Okay, and since we are close to our chapter 1, let's consider this is our normal reference system. Okay, now we see on the side This is X. This is Y. So we're going to have one force here, two here, and one here. So I have W1, W2, W3, and W4. Now, of course, we have buoyancy here. Yeah. So this is B of X. Now, somebody say, okay, wait a minute. And what about the weight of the hull? Well, we're going to neglect it. We're going to consider only these four and these as the forces acting on the beam. Okay? Now, this is something that Misayo solved a couple of weeks, last week, right, Misayo?
Yes, doctor.
So we have something like this. Like this. So we have longitudinal variation, we have a jump, longitudinal variation, we have a jump, longitudinal variation, we have a jump. There. Okay, so this is V. Similarly, you go for the bending moment. Something like this. And there is some changes in curvature in each of these points, but I don't want to draw too much. So that's basically the problem of the hull. See, the ship is floating and everything is fine. Now, there are a couple of things here. Now let's go to naval architecture, right? Here, you see that I have drawn the distribution of the weights in a symmetric way. So about here, we're going to have the center of gravity. Yeah, about here, we're going to have the center of buoyancy. So this is the total force, like that. Okay, so total force is going to be the summation of Wi. And this thing here is going to be the integral of V of X dx. So L over 2. Are you with me, people? Okay, now, to calculate B, you need the draft. Calculate the draft, you need to equate the weight, which is this, with the buoyancy. I'm going to try to flotate up to half of the diameter. Okay. So you can calculate this. You have this, these are data, so you should be able to calculate this. Okay? So let's write it here. P of X is going to be B of X, and eventually this is going to be a constant since we're going to float with no trim. Okay? And then we're going to have minus, since we have 4 concentrated forces, we're going to have something like this. Okay. Okay. So this is constant because we are using a distribution which is symmetric with respect to midship. So you could integrate the two, the P of X, and calculate the V of X, integrate V of X to calculate M of T. Now, what is it that we're going to do? This is what we did. In here, about here, let me change color. We make a cut. So it's about here. Okay, this is not new. Okay, this is not the original idea. In the past, people did this and put it this ship models with these cuts in a towing tank, and they generated waves. So in order to do these calculations. So what do we have here? In here, we have installed, not me, we, Mr. Yangare and friends. They installed, oh man, I have to draw here. Okay, I'm going to draw just on it in a side view. Okay, this is the two pieces. So here we have a cut. This is completely closed. Water is going to be up to this point, more or less. And here we're going to start at a small angle. Okay, and here we're going to connect the two pieces with a load cell. This is a load cell. There's going to be some small holes here. Something like that. So here we're going to have a signal, and this signal is going to be proportional to the force between this and that. Can you tell me what this is? Mr. Aizaga, what this is? What is this? What is this? Mr. Aizaga, could you please tell me what this is? This and that. Mr. Aizaga is not here. Ms. Flores, can you tell me what this is? Ms. Flores? Can you tell me what this is?
I don't know, doctor.
No? Anybody? Anybody what this is?
Shear force.
Exactly. This is the shear force. The shear force. So let me go back. Let me go back. Okay. So we apply these forces, and once we get equilibrium, okay, so they gain some draft. Forces upward, forces downward, they equilibrate. So we go and make a cut at different points. On those points, to have equilibrium, we have, this is what we call the section method. We have shear force and bending moment. In this case, we install this load cell, and supposedly should give us the shear force. Okay, so about in this figure, more or less, this cut corresponds to this point. So this value here, which we calculated solving our equation, it's going to be compared with the value that we obtained with our load cell. So far, is there any question? People, is there any question so far? No. Okay. Now, the thing is that we have this beam, and according to the position where we apply the force, we have this reduction because we have the buoyancy, and then here we have a jump. Okay, this value, this jump, is equal to this force. Now, after this, we have the reduction. We have a jump. Now, if we have, in this point, we have the cut, then we're going to see, we're going to obtain this value here, or something similar. Now, what happens if I change the position of this force a little bit to the right? Okay, so if I do that, we're gonna have something like this. Okay, let me put this to the right-hand side. So here I have the cut. So now we're gonna have something like this. And the value is going to be different than this one. Okay, so this is something that I want you to check. Okay, and now what happens if I change this a little bit to the right? What do you think? What happens with this value here?
It will increase.
Is it? Let's analyze it. This, instead of here, I'm going to apply it a little bit to the right, and I go like this. What happened? What happened? Mr. Carranza, what do you say?
Good morning, doctor. And this part is increased in different areas in the chart.
No. You see here, I have this increment when I have the force here.
Yes.
This slope depends on the draft. Now here, this line is the same as this one. But instead of stopping here, it goes up to here where you have the applied force. But in this point where we have the cut, there will be no change. It's a little bit tricky, I mean, and that's why it's something I want you to learn. Okay, now this is your theory. Let's see if we can make it work. Okay. Is there any problem so far, people, with with what we are going to do?
Doctor, I'm sorry.
Yeah, go on.
What are the arrows for? You move
What are the what? I'm sorry?
the arrows.
The arrows.
The
The arrows are the force. Okay, here is W1. So I'm showing you this W1. So this is W1. It's the same W1. It's the same W1. But what I do is I move it along the x-axis. The other three forces, this is W2, W3, and W4 is about here. So when I move this a little bit to the right, I have to move this a little bit to the left so that the trim will be 0 or more or less 0. So yeah, this is the same force. It's a weight, right? But I just move it in the x direction. Mr. Dominguez?
Yes, doctor. But the load cell doesn't move, right?
No, the load side is there. So, for example, in one point, you have this W1 on this side. Then when you're here, you have the load, instead of the weight, instead of being here, this is W1. We're going to move it to this side. According to our analysis, once you move it to the right, there should be no change in loading force. Let's see. Theoretically, that's what should happen. Okay? Any more questions?
Yes, doctor.
Yeah.
Do we have to take the tube over the boundaries?
That's not the question. The tube is floating, and if you assume that the weight of the tube is small, the 4 weights are the forces pointing downward. And you calculate the forces upward, which is the buoyancy, so you have equilibrium. The 2 forces have the same value, and the two forces are aligned. In this case, what we do is we put two forces on the left, two forces on the right, so we have a no trim.
So, not trim. So
Yeah.
in both ends,
You want trim? You want trim?
no. So in both ends are free.
Yeah. Both ends
Nobody
are free.
gonna take it for the tube and
No. The tubes are free. This is the setup. Okay, so you will just put it on the water. We have to be very careful, people, because this has a connection between the two parts. If you pull it from one side, suddenly there's going to be an extra load, and it's possible that this just breaks up. So every time you hold it, two people have to hold it, one from each side, and then put it gently on the water. Yeah, this is equilibrium. Summation of force is equal to 0. That is the force, the summation of force is equal to the buoyancy. And the two are aligned. So you take moments with respect to this point, the other force has no arm, and that's going to be 0. Yeah, and to calculate the distribution of loading of buoyancy, we're going to consider that there's no trim. Let's see how it works. And then next semester, we can add some trim. Santos?
yes, and the picture.
Okay. Now, what is it that we're going to do? This is what we're going to do. This is the first step. This is the first time we do this. So we have to be patient. That's why we ask the people who are going to be in the first hour to come, not to come at 9, but to come at 8:30. Okay, so I suspect that put this at, okay, the connection, some holes here. So you can manipulate the weights from above. Ends are closed. So we're going to be floating up to here, more or less. Remember, this load cell is connecting the two pieces. So we have to be careful not to break the load cells. They are aluminum, so they are not as strong as steel. After we put this on the water, hopefully nothing happens, then we install the new weights. Okay, so we install weight 1, I'm sorry, weight 3 and weight 4. And then we install weight 1, I'm sorry, and weight 4 about here. And we are supposed to be floating more or less up to here. So we can measure the draft. We should be able to calculate the buoyancy force. Okay, now when we install, I'm sorry, I forgot. Let me go back. Let me erase. Okay, here, this is very important. We have to 0 B. So in this condition, we assume that the weight is neglectable. So this is just like in the air. Hope that this doesn't bring much of an error. Okay. So here, this is our reference situation. So what I'm saying is that we can start recording in this position. So if this is time, okay, we have a two signals because we have two load cells. Okay, I'm going to show this. So this is voltage. Okay, it's floating. Now, when we install gently, always gently, please. Okay, this is going to increase. So, and eventually it's going to be in equilibrium. Okay, now after doing this, what we need to do is change the position. So we go from here, we put it in here. So there's going to be a change in here. Let me go back. So you put it a little bit to the right, it's going to increase, yes. Not much, but it's going to be an increment. Okay, then comes the interesting part. This up to here. And then I'm expecting a larger increment. Since we want to check that when we move it to the right, this doesn't change, yes, let's do it. We go a little bit to the right, a little bit to the left. There should be just a wiggling here, like that. Questions, people? Questions so far? Okay, then Mr. Yandere and company, they developed a curve that converts voltage in weights, in forces. And with that, we are going to be able to calculate the shear force here. Questions, people? Of course, this has to be a little bit, I mean, the scan rate, we have to set this scan rate, or Daniela, this scan rate cannot be too long because we're going to take some minutes to do this. Okay, that's probably about 10, 20. Because after this, we have to go back, try to see if we can return to the zero position. Okay, that means that we have to move, and then we take gently, we take all the loading, and we should recuperate the value of the voltage from the load cells from the beginning. Questions, people? People, is there any question?
I have a question. The max force applying this pin, what is the number?
We don't know. The problem is that I have problems because we do not know when you have the load cell, right? You have the two sections very close. You have the load cell. If you have very large bending moment, it is possible that they rotate and they touch at the bottom. And of course, we don't want that. So we have to be careful. So at the beginning, I'm going to apply a low force. Let's see what happens. And if we can apply a larger force and we have to check that when they rotate these two sections, they don't touch up and down, we can increase the force that we need to apply. The two load cells have a capacity of, do you remember, Andy?
10 kilograms, I believe.
8 kilograms. So we have a capacity because we have two load cells in parallel. So we can support up to 20 kilograms. But the problem is that they are joined to covers of wood, and we could have some deformation. So that's why I would like to start with 1 kilogram for W1 and W4. Then we can go on and see if we can increase this value. Any other question? This is primary behavior of the ship hull. Eventually, what we could do is we have several models. We could try to cut for 3 pieces, and we can do something similar. But in that case, the geometry is going to be much, much more complex. So the calculation will take much, much, much larger. So that's why I prefer to work with this simple experiment and see what happens. I was thinking that it is possible that we could do this and make another cut in the central part and try to measure instead of shear force, try to measure bending moment. So we could measure a shear force about 1/4 of the length, and about in the central part we would measure bending moment. But that's for the future. Let's see what happens in this case. Okay, if there are more questions, then that's what we're going to be doing tomorrow. So please, those of you who come for the first in the first itinerary, please try to be here, try to be in the lab at 8:30 so we can set everything up. And please, people, we have to be careful because we have to do things like this being connected by a little thing in aluminum. Okay. Okay, before we break, in the lab, even though there's not such a large weight, we suffered a small accident the last time we worked in the lab, right, Miss Santos?
Don't remember that.
Are you okay? Are you okay now?
Yeah.
Are you okay? Okay, so from now on, in ship instructor, every time you come to a lab, you have to wear boots. If you don't wear boots, sorry about you, Maria Daniela and Andy. You have to wear boots. Okay? Nobody doing structural experiments can come without boots. Don't have to be just extremely boots, but have to be boots. Okay? But in this case, it was in a small accident, right? I don't want to think that, for example, if a weight drops on your feet, they can break one little bone. We don't want that. Okay, so tomorrow and morning and afternoon, nobody can come to the lab without boots. Okay. Okay, finally, on Thursday, we have the evaluation. Okay, we have some problems because some students, they have to come, they have another evaluation at about 12. Okay, so what I decided was to move a little bit our quiz number 3, to start at 9 a.m. 9 a.m. I posted 2 or 3 days ago an announcement in Aula Virtual specifying that you have to be in the university at 9 a.m. to start the quiz. Okay, 9 a.m., not 9:10, 9 a.m. So in this way, we can finish at 11, and those who are going to take another quiz, they have at least 1 hour to take a break and maybe have a coffee. I can invite you to coffee, those who you want. I can share some crackers or something like that, so you can recuperate your energy to take the next test. Is there any questions about that? It's a closed book. It's a closed book. Up to now, what I have thought is that we're going to have a first part, some short questions, multiple choice. The second part, problems to be developed. Any questions about this, people? Chapter 4 only, chapter 4.
How much time? 1 hour for the quiz?
Oh, no, at least 2 hours. See, I think I haven't completed. See, I've started. I've done a sketch of the quiz, but I'm thinking that it should take about 1 hour and 45 minutes. So the problem is that, as I said before, after that, there's some students who are going to take another quiz, and it's very demanding for them. So that's why I'm going to make it a little bit shorter. So 1 hour and 45.
Okay.
No questions.
Doctor,
9, 8. Yeah, go on, Dominguez.
with Timoshenko too.
See, the material of chapter 4 in general,
Okay. Yes.
the
thank
material
you.
in chapter 4. So basically, what we have to do is review the material that we presented in class, examples that we developed in class, the lab report, and the homework, the assignment number, I don't know, 5, I think. Yeah, that's the material you're going to be reviewed. No questions? Okay, I'll see you tomorrow and on Thursday. And on Friday, those of you who want to do some sport, yeah. Okay, people, bye-bye now.
Thank you.